If you can point out a single unifying theme to all of the statistics that we do here in this class and elsewhere, it's about fundamentally answering two questions. And those two questions are given some information, one, what sort of prediction can you make? And two, how accurate that prediction is. So, in the case of hypothesis testing, for example, if you or rather say in the instances of confidence intervals, you want to predict the population mean of some random variable. So you gather a bunch of data, you do your analysis, and you're able to make two statements. One is a predictor for the population mean, and two, uh, the confidence level and the interval that goes with that, which tells you more or less how good of a prediction or your predictor is. So we're going to be doing something fairly similar with linear regression, but it's not going to be quite in the same flavor as in the hypothesis testing questions we've worked on. So let's start again with a hypothetical scenario. Let's say you have a bunch of students in the class, and we have uh, there's an upcoming exam, and so there's two questions, or each student in the class prepares for the exam. So each student spends some number of hours preparing for exams, and each student receives, after the exam, receives some sort of score. All right, and so let's go ahead and plot a bunch of uh, points for this. And I'm not going to go super overboard with a lot of points, just trying to make a point about how what we're talking about and how it works. So let's say one student prepares for 15 hours and receives a score of a 98. A different student prepares for 16 hours and receives a score of an 80. A different student prepares for 12 hours and gets a score of an 85, let's say an 88, and so on and so forth. Let's say someone did 14 hours and got a 75. Someone did 7 hours and got a 99. Uh, 8 hours and a 77. Let's say 420. And let's do one more. It's going to get a little bit hard to read at a certain point. So that's about, let's say, 1395. All right, so we have all of these students and they have all of these scores. Uh, it's a pair of points, or sorry, it's a pair of values which makes a point, right, in the 2D graph. So you can think of this as being x values, the hours preparing for an exam, and the score they got in the exam is the y value. And so, as a researcher or as a student in this class or as a teacher, you might look at this cloud of data and you might ask yourselves two questions here, and these are important. Question number one is uh, all right, can we predict, right? Can we predict if a student studies, say, 10 hours, what their score is likely to be on this exam? And then the second question is, how accurate is that prediction? And this is an important question because uh, if you're able to super accurately predict people's scores based on how many hours they spent preparing, that tells you that tells you that the hours preparing for the exam, that might be the most important factor in determining someone's score. On the other hand, if the uh, if the predictions are not very accurate at all, then that tells you that there's a lot of other factors that determine what makes up a student's score and not just hours preparing for the exam. So the thing to remember is that the world is a really complicated, multivariate place, right? And so when you think about your own lives and the kind of things that say go into uh, a class or taking a test or doing something like school related, there's a lot of different factors, right? It's not just how many hours you spend preparing for a test that determines the outcome. A lot of different things factor into it. And so what we're measuring here is just the relationship between these two variables and ignoring the dozens or hundreds of other variables that might make a difference here. And so we want to also know, right, how much uh, of a factor is the one variable a predictor for the other variable. And so uh, let's go ahead and parenthetically make some notes. So our goal here is, given a value for x, we want to predict y. Right, given some number of hours to prepare an exam, we'd like to know what the likely score is going to be. We want to measure accuracy of the prediction. And last but not least, related to measured accuracy, so it doesn't get its own bullet point, is how much of y is predicted by x. Right? So you can throw any two variables together, but if y doesn't do a very, or x doesn't do a very good job of predicting y, then uh, we should be able to detect that. Like if I were to throw people's exam scores up here and I don't know how much chocolate you ate in the previous week down here, there really shouldn't be much of a relationship, and whatever analysis we do should tell us that, right? It should be consistent with that. All right. So, uh, for the purposes of this particular question, we are focused on linear regression. So we're going to assume in this class, y is a linear that's not really the right way to phrase it. The right way to phrase it is assume x, y have a linear relationship. You might imagine that it's certainly possible that there's a lot of different types of function, and it's certainly possible for x and y to have a linear relationship other than linear, right? Like a curve or an exponential sort of growth or a parabolic relationship. Those are all things that are possible if x and y have a relationship, which they might not. And so this is a prerequisite to doing a linear regression uh, problem. We can see if we look in the textbook that one of the criteria for deciding whether or not something's linear is to look at the is to look at the cloud of data and see if drawing a line through that cloud makes sense. In some of these cases, like this one here, a linear projector may not be the appropriate way to try to figure out what x and y's relationship are, and you're best off not doing it. And so you want to make sure of that first. So, and of course, though, if we do have a linear relationship, then linear variables are determined by a slope and a y-intercept, right? So the standard form is that y is predicted by a linear expression. So in our case here, I have that y is estimated by beta 1 x plus beta naught. So this is uh, the slope. This is the y-intercept. And so I'm not going to belabor all of the old, how do you draw lines sort of math that we've done in uh, middle school or high school or wherever we did it. But just to kind of briefly remind us what those things mean. If I were to draw a line, blah. Okay, so there's a line. The y-intercept is the height here. All right, so basically when x is 0, right, then all you get is beta naught. So we can actually specifically call this point what it is, 0 beta naught. And then beta 1 is the slope. So the slope is however many units you go forward, however far up or down you go per unit. So often denoted or called rise over run. Right? It's just a change in y over the change in x. All right. So let's go back to our original picture here. So job number 1 then is for us to look at a cloud of points like this and say, all right, first of all, what sort of a line should I draw through this cloud of points, right? Before I can talk about how good of a prediction something is, I need to make the prediction first. So what is the best line to go through this cloud? i.e., what's the best choice for beta 1 and beta naught, so that it most accurately represents this picture. And so let's think about what sort of a line would make sense there. So I'm going to go ahead and I'm just going to draw a bunch of points. And then we'll just throw a bunch of points out there. There we go. Bunch of points. And so look at that bunch of points and you say, okay, what sort of a line could I draw? And so the first thing to note is that you can draw any line you want and it will be some sort of a predictor, right? But we actually want it to be a good predictor. So what does a good prediction mean? So let's say I do draw a line. That's probably not the right line, right? But let's just say that that's our line. So let's call this line L of x, right? And so L of x is the linear function that represents that line. And let's take a look at this cloud of points. Now, when you have a big old cloud like this, no line, no single line is going to be a perfect predictor, right? You're not going to draw a single straight line that goes through every single one of these points. You have to do your best. So, what we should notice though is that some of these points are overshoots, right? That, or undershoots rather, that if I were to pick some x value down here and it uses this line to predict a y value, that y value is less than what uh, these points actually are, right? Or their actual y values. On the other hand, for a whole bunch of these, there's overshoot, right? For all of these points here, the oops. For all of these points here, for all of these points, uh, I put in their x values, and what the line tells me the y value should be is a lot more than, in many cases, what the y values of these points actually are. And so this is inevitable, right? There's no way I could possibly draw a line uh, where there is no error. But what you don't want to do, say, is draw a line like that and call that your prediction, where all of the error is positive. And you don't want to draw a line like that, uh, where all of the error is negative and everything is an undershoot. You it's inevitable that there is error, but you want all of the errors to cancel out. You want to shoot like straight through the middle of the cloud so that all of the positive error and all of the negative errors cancel each other out. So let's go ahead and give these things a name. Let's say that all of these things here, both things like that and things like that, are errors. So in particular, given a point, uh, xi comma yi, so that's one of the points. The error for the point I is going to be the actual value of y at that point minus what my projector says y should be. Right? So that's either a distance here like that or a distance here like that. So it's positive if y is over the line and it's negative if y is under the line. Right? And so some conditions is that the sum of the errors has to be 0. All right. And so that tells you something about what sort of lines we can draw. We can't draw a big old line up here. We can't draw a line down here. We strictly speaking probably couldn't even draw this line because it does seem like the undershoots vastly outweigh the overshoots. Uh, but let's go ahead and keep this line here just because we will have all of this drawn, and let's talk some more about conditions on what the best fit line needs to do. So all of these errors, let's say all of these errors cancel out. That's great. Would that be the only line that could do it? Well, it does seem as if you could cleverly draw a line like that where all of the overs and all of the unders uh, cancel each other out. It seems like you could. Oh no. Oh, fixed it. It does seem like you could go the other way, right? And then uh, fix a slope like that and draw it in a way so that all of the overs and unders cancel out. So clearly, it's not enough just to say that all of the errors are zero. Let's go ahead and leave a very egregious possible line here, and let's compare these two lines. What makes say the red line look like it's a better predictor than the purple line? Well, with the purple line, the errors are a lot, right? Like if I take this point here, its error is all the way up here, right? The purple line predicts that y value to be up here, where in fact it's way down here. And similarly, it takes a point like that, and we find out that it's way overshooting here. So even if all of the errors add up to zero, the undershoots are huge and the overshoots are huge too. And we'd rather there be as little over or undershooting at all if possible, right? Which it's not, but we'd like those to be minimized. So that leads us to our second condition, which is that the sum of the errors squared is minimized. Right? And you want that to happen because whether or not the errors are positive or negative, once we square them, those values are now positive. The larger the magnitude of the errors, the more the square is. So you're looking for a line that minimizes the magnitude of these errors squared. And then it turns out, and I won't go into the details of this because it's fairly complicated and it involves math that are somewhat beyond the scope of this course. But it turns out that that's enough information to determine a unique line. And so, in the spirit of, practically doing things with data in this class, we're going to use technology to go ahead and figure out what this line is for us. So, on the website, there's a linear regression calculator. And here I have an example already plotted. What we have here are years after 2000 as our x values, so starting in 2004 up until 2013, and the y values are the FBI crime statistics for murders in the United States per 100,000 people. So in 2004, there were 5.5 murders per 100,000, 2005, 5.6 murders, and so on and so forth. So in 2013, 4.5 murders. And when we run all of that, we see that when we try to fit this data into a linear form, we have parameters, a slope minus 0.144848, and y-intercept 6.4 or so. And the purpose, again, of doing something like that is to make predictions, right? So according to this extrapolation, in the year 2018, there should have been 3.794 murders per 100,000 people in the United States. In the year 2020, it should be, 3.5 murders per 100,000 people. So let's go ahead and maybe put in the data from our example here. So I'm going to drag this off screen and start entering this data in. Uh, so or maybe it's best if I put it on here so we can see how I'm doing this. So one of our students studied 13 hours and got a 95. Another student studied 4 hours and got a 20. 8 hours and got a 77. 12 hours and got an 88. 7 hours and got a 99. 15 hours and got a 98. 16 hours and got an 80. 14 hours and got a 75. And so we can see the distribution of scores here, right? And so this is what that plot of data looks like. These are the points. And what it tells us is that this line has parameter slope 3.484 and y-intercept 40.24 or so. So that's what this line looks like. And so let's go ahead and ask ourselves what the predictor is for someone, or what the prediction is for someone, say, who studies 10 hours. I think that's the question we asked ourselves. So if someone studied 10 hours, then what we're basically doing is taking a line with y-intercept 40.2405 and slope 3.484 and asking ourselves what happens when x is 10. So we zoom in, here's x is 10, we go up here and we hit this point and we wonder what that point is, and we can use the calculator to help us do that. When x is 10, the y value is 75.081. So it predicts that if you study 10 hours, you'll get a 75. All right, so that answers the first part of our question here, which is given x, predict a y. And so we have to talk about our second part of this question, which is how accurate of a prediction is this anyway? And just looking at this, we should probably not feel great about its predictive ability. Every point is an overshoot or an undershoot. This point is a massive overshoot, right? So we should think that, all right, studying certainly has an effect, right? It definitely contributes to the score, but it's certainly not the only thing determining what the score is, right? That's just sensible. So, that's where these parameters here, the r and the r squared, come in. And so r is the correlation coefficient. And what it does is it measures the relationship between x and y. And so there are good examples in the book. I'm just going to use those because they're oops, they're already there. Excuse me. Sorry about that. All right, there we go. So I'm just going to go ahead and jump down to where we discussed this in the text. Because they're pretty good examples of correlations right here. And so the correlation coefficient ranges between 1 and negative 1. 1 is a perfectly positive relationship, negative 1 is a perfectly negative relationship, 0 would be no relationship at all. And so we can see here, starting at 1, as r decreases, we get less and less cohesive positive relationships. And then at 0 would be no relationship. And then as you go below 0, it gets to be less cohesive negative relationships, all the way to a perfectly negative relationship. And so we should note then that maybe parenthetically, like r ranges between negative 1 and 1. And so if you didn't care whether or not the relationship was positive or negative, you just wanted to measure the strength of the relationship, the way we measure that is with r squared. And so, right, 1 and negative 1 are different, but if I squared r, then I get 1 and I get 1, and those are both positive relationships, right? And so the closer you are to 1 or the closer you are to negative 1, when you square that value, the closer you are to positive 1 either way. And so the stronger the relationship was, positive or negative, the closer to 1 the r squared value is. And this is really important to note too. R squared also tells you exactly how much of y is predictable by x. Right, so r squared is a value between 0 and 1, so it tells you either 100% of the time you can determine what y is just by knowing x or nothing else. If it's something less, if your r squared is less than 1, what that tells you is, all right, whatever determines, makes x true, though an r squared proportion of that influences y. The rest of what makes y what it is found elsewhere and not to be found within x itself or in the things that make x true. Right? And so if it's 0, it means it's totally independent. It means that your x value tells you absolutely nothing about what y does. So let's go back to our example here. We have that r is about 0.58 and our r squared is about 34.01%. And so what that tells us is that in this particular case, what that says is study time is a 34.1% predictor of the score. Which means that there's another 66% of what makes up the score lurking out there somewhere. Okay, so at this point, it behooves me to give some very important warnings about when it's appropriate to use linear regression and when it's not, and what linear regression means. And so this is a pretty common gift now amongst people who teach statistics, and it's showing a bunch of different possible plots of data points with different x's and different y's. They all the plots have roughly the same mean, roughly the same standard deviation. You can see some changes here, and roughly the same correlation, but they're totally different graphs, right? And so you should never ever pretend that the correlation uh, information paints a perfect picture of what's going on with your data, right? All of these different plots have the same parameters, and yet we would probably consider them to be very, very different. So that's just a warning in general. A second warning is that I'm going to write this out here, that correlation is not the same as causation. And what I mean by that is just because two things are correlated doesn't mean that one of them causes the other. So, a good example one of my Stat 341 students came up with last semester is, does wearing shoes when you go to bed cause headaches? Why would you think that? Well, it turns out that people who wore shoes to bed were more likely to wake up with headaches. And so maybe initially it might be worth it to consider the possibility that sleeping with shoes somehow affects the way that your body's circulatory system works or something, and then you get a headache. But it turns out, so let me just draw this out. So maybe just a quick little graph. Proportion of people who wear, or the proportion of time you wear shoes maybe, and the proportion of times you get headache. Get headache. And there's some positive trend line. All right. So when they dug deeper into the background of why this was, it's because if you wear shoes when you go to sleep, you're more likely to have passed out drunk. And if you passed out drunk, you're more likely to wake up with a hangover and therefore have a headache. And so it turns out that if you're totally sober and you just wear shoes when you go to bed, that doesn't really affect the chances that you get a headache. Nor would having a headache for like some other reason make it more likely that you wore shoes. They're both driven by an underlying phenomena, being drunk. Right? And so it's important to note that when you observe a pattern or relationship between two variables, it's just a pattern. and not to read too deeply between these sort of relationships unless you have a really, really good reason to. In general, it's best to assume that at best that the two variables in question have a common cause rather than that one causes the other. And to sort of highlight this, there's a bunch of examples of very, very strongly correlated variables here on this website, spurious correlations. So you can see that people who drown in pool correlate strongly with how often Nicolas Cage appears in films. The more cheese people eat, the more people die by becoming entangled in their bed sheets, and so on and so forth. So there's a whole bunch of these, and they're all completely ridiculous. But it's important to point out that, the world is a big place with a lot of variables. There are also just coincidences, right? Think about how many variables there are in the world. It's every possible thing that could ever be measured, and that's innumerable. So some percentage of them are just going to line up for no reason, right? And so that's something else you need to worry about too. When you see correlation between two variables, it might not mean anything at all. Um, and so those are just precautionary sort of stories as you go forward and do this sort of statistical stuff. All right. Um, I think that's the last video on content. I'll still make videos about specific problems and follow-up videos on concepts that people ask for, but I think I'm done for the moment. So uh, thank you very much for watching, and please let me know if any questions or comments.